Last time we have talked about cubic spline, which is a method to interpolate the data points, but it is not really a statistical method since it has to pass through all the points that lead to the problem of overfitting. So this time, let's look at smoothing spline to see how we improve on that and how it can fit into noisy data. Okay, so for the problem setup, we are going to be using the same setup as last time, which we start with paired data xi and yi, where I goes from 1 to n. And then I should emphasize that xi uh, are real numbers, while y are also real numbers. So this is one-dimensional case. And then, so the goal here is that we want to fit a curve that the curve that best fit is a line without passing through each point, right? Remember that last time our cubic span has to pass through each point, and so that could lead to overfitting for real problems. But smoothing span, hopefully that can handle noise. That can handle noise by just kind of balancing the by trading off the data fit versus the smoothness of the curve. So so the goal here is to find function f that trade off fitting and smoothness. Okay, so what we like to consider here is that we are consider a penalized least square problem. So our objective here is to find the function f. I should probably okay. Let me just write down here, right? That yi is equal to f of xi plus epsilon I. So that's going to be the relationship between x and y. And the penalized least square is going to be something like this. It's f star equals to arg mean of f, and then summation I to 1 of n y minus f xi square plus lambda the then f prime prime of x square dx. So that's our objective. Okay, I should also say that this data set is sorted. That means x1 is smaller than x2, smaller than xn. So that's the sorted data. And so this is the penalized least square. Let's see how we interpret them. So the first term here, this is our standard least square, right? This is a sum of residual square. Should put it here. Sum of residual square. So this term actually equals to 0 for the cubic spline we had last time. But for the smoothing spline, actually, we don't want to we don't want the data to pass through every point. Okay, we don't want we don't want yi equals to fi for each point. So that's the goal here. So this is just something we put it into optimization. So the lower this term means means that the data points will be just closer to the curve. So the second term here is what's making smoothing spline interesting. So this is called this is a penalty for curvature. Okay, so let me just explain what does this mean and why the second derivative can be thought of as a curvature. Okay, so let me just go down a little bit. Okay, so let me just draw something here. Let's think about the quadratic function. Okay, uh, and let me just draw two curves here. and another one like this. Okay, let me say that this is a function of y equals to x squared, and this is y equals to 1 over 10 x squared. Okay, so if I just plot data points 1 here, this is this is 1/10 on here, and here on the other curve, the yellow curve is 1 on the y value. So apparently, like visually, we can see that the yellow curve has more curvature than the green one, right? Because it curved more. And if we just do the second derivative of this thing, the second derivative this for the yellow curve is going to be 1, and for the green curve, it's going to be 1/10. So this is a lot smaller than the yellow one for its second derivative. So what's gonna happen when the second derivative goes to zero? So that's when we'll get a flat line. We'll get a straight line that's gonna be second derivative equals to 0. So this is why we want to penalize on this term here. We want this if the second derivative is closer to 0, that means the curve has less curvature. Okay, so let me just okay. So that is the objective for this for the smoothing spline. We want to find the function that balances the two. And when you have like a random curve like this, for example, when you have a random curve like this, you can think of this integral here as an approximation of a bunch of quadratic functions. So let's say that I start at A and end at B. And then what we are basically doing is that we are approximating this function with a bunch of local quadratic functions. And then we're basically like summing over each point to see like how much curvature there are in this in this entire curve this entire blue curves. So probably see that intuitively like the more turning the more turning this curve have, then that means the total the curvature penalty is going to be more, right? Where in contrast to when you have like a straight line, so that curve has like no curvature. Okay, so that's really the intuition about smoothing spline. And now let's think about how to solve this problem. Okay, so how to solve this problem? So first, we must know what is the space for all the functions that are that we can optimize. Okay, so if we just gonna put down this penalized d square term, if we just consider this penalized d square, then f is really have a huge space, right? This is called C2 space. C2 simply means that the space is means that the function is twice differentiable. Means that the second derivative of the function is continuous. So that's the C2 space. So this is a huge space because it basically contains a whole bunch of functions like like our spline function, like the like the polynomial function we have, and then also like basically all the function we know, right? The sine function, cosine function, like it has a whole bunch of things. That's a really large space. So what we like to consider here is to reduce the functional space to make f more specific. So what we can do is that we can assume that f to be piecewise cubic. So this is just like last time. We already see in the cubic spline that the piecewise cubic function is actually nice because we can make the first and second derivative both to be continuous. So that's the specific set of functions we're going to use. And for this type of f, we know that there are four times n minus 1 parameters, right? Because when n data points, the n data points give us n minus 1 segment. And then each segment is parameterized by a different cubic function that give us 4 times n minus 1 parameters. Okay, so this way our space is about reduced comparing to to all the twice differentiable functions. However, I must emphasize here, or just give you a spoiler. So actually, f can be solved directly from variational calculus. So this is something we're gonna do in the future, and it turns out the best result from variational calculus is just the pairwise cubic function. Sorry, piecewise cubic function. So we are not missing anything here. But in this particular video, let's just assume it to be a piecewise cubic function, and so that means we can write down the function f in this way: f of x equals to fi of x equals to ai cube, sorry, ai x cube plus bi x squared plus cix plus di when x is in between the segment I that go from xi to xi plus 1. So that is the function we're going to assume it's a piecewise cubic function just like last time. Okay, so now before solving this, we should also be mindful about the constraint of the problem, because just, if we just do it in this way, there's no guarantee that the function is going to be continuous. And, we also need to make sure the first and second derivative to be continuous as well as the boundary conditions. So that doesn't change. But what's changing is that now the function f don't have to pass through every point like cubic spline. We have a constraint problem. We have an optimization problem for that. So let me just write down here about the constraints. So we have fx to be continuous, and then f prime x continuous, f prime prime of x to be also be continuous. And also we have the boundary condition of f prime prime x1 equals to f prime prime xn equals to 0. The second derivative vanishes at the boundary. That's the same as cubic spline. Okay, for the next part of the video, I'm just gonna introduce a simpler example with 3 data points. But when we have n data points, it is gonna be the same framework. So example, let's consider 3 data points of -1, y1, and then 0, y2, then 1, y3. And then let me just rewrite the objective function we have. And f star is going to be arc min f yi minus f of xi square plus lambda a to b, and then f prime prime x squared dx. Okay, I should also emphasize here that a equals to x1 and then b equals to x. So that's really the entire region for the curve we want to fit. Okay, so in this reduced problem, f only have 2 segments. So that means fx equals to a1x cubed plus b1x squared plus c1x plus d1 and then x in between x1, x2. Sorry, this is I'm just gonna do 0, 1, and then a 2x cubed. Okay, so here I've only have two segments in it, and maybe let's just first do the constraints. So the constraints becomes so the first constraint is that f is continuous. So that means at point 0, these two functions has to equal to each other. That give us d1 equals to d2. And then f prime of x continuous. That's we're just gonna take the derivative of this thing. Maybe I can just write it in here. Let's do the derivative real quick. So so f prime of x is gonna be 3a1x squared plus 2b1x plus c1. And then that's going to be 3a2x squared, 2b2x plus c2. And that gives us c1 equals to c2. So then we have f prime prime to be continuous. And then let's do it like this. And 6a1x plus 2b1, 6a2x plus 2b2. So this means b1 equals to b2. So that's the three continuity conditions. And then we also have the boundary constraint. Okay, so the boundary constraint, and so that's going to be two constraints we have, and f prime prime of x of -1 equals to 0. That gives us minus 6a1 plus 2b1 equals to 0, and then f prime prime of 1 equals to 0. That's give us 6a2 plus 2b2 equals to 0. So you can see that all of these constraints are just linear constraints. So let's just translate this into a matrix notation. Let me just define a vector beta here containing all the unknowns we have. That's going to be A1, B1, C1, D1, and then A2, B2, C2, D2. That's this is a 8 times 1 vector. And then we can also define the matrix A here to be because we have in total of 5 equations, right? And we have 5 constraints, so 5 equations. So A is just going to be a 5 times A matrix. And then in the end, we'll have A times beta equals to 0. That's our constraint. And you can just easily translate those those equations into the A matrix here. I'm just going to do one. Let's just do the last one. This one here. So we're gonna have first 4 terms equals to 0, and then we'll have a 6 and a 2 and 0, 0. Okay, you can do everything here, right? For example, this one is just gonna be 0 minus 1, sorry, minus 1 0 0 0, and then 1 0 0. Okay, so you can fill out this matrix here. But the point is that at the end, we have a linear constraint of A beta equals to 0. So that's a constraint for this problem. And now let's after we're dealing with constraint, let's think about let's see how we can simplify the optimization term. So let me just grab this equation. Okay, good. So now let's consider how we can simplify this optimization problem. So let's just separate out the two terms, right? This is the first term and the second term. Let's just do it one by one. Okay, so for the first term, and for the first time, I just plug it in to see what happens. So it turns out this looks a lot similar to the basis expansion we talked about before. So we can write it out as a linear problem. I think I'm missing a summation here. So we can write it out as a matrix form by defining this augmented matrix Z. So here's how it's gonna work. So Z, we can define that as a matrix containing 3 data points by just augmenting it. So we can do it like this: 1x, x squared, x cubed, and then let's just see. Just fill it in. The first data point is going to be -1. And the first data point is just going to be -1. So we just put these numbers in as 1, -1, 1, and then -1. And I actually remember that the Z matrix has to be multiplied by the beta matrix, right? The beta is a A by 1 matrix that contains both A1 and A2, right? So it's both the first and the second segment of our cubic spline. So that means this matrix Z here has to have 8 columns. So we're just gonna do this like point by point way, point by point way, and let's put the second value as a second column. That's just gonna matches with with a second cubic, and so we can view it in this way. Okay, so we put 0 here. We're just gonna repeat this, and that's gonna be 1, 0, 0, 0. And then the third point, -1, we have 1, 1, 1, 1. So that way, when you do the matrix multiplication of Z times beta, we can get exactly F1 of X1, and then F2 of X2, and then F2 of X3. This is just F of X1, F of X2, F of X3. Okay, so that means we can translate the first term into a matrix notation as this, right? So this whole term here becomes y minus z beta transpose y minus z beta. This is nice. This is really nice because it looks just as our linear function, as our linear optimization function least square. Now let's see what we can do with the second term. So the second term, remember what we have is this, right? A to b, and then f prime prime x square dx. And then recall that f prime prime of x equals to 6a1 x plus 2b1. And then that's for x equal to x in between x1 and x2. This is 6a2x plus 2b2. This is for x equals to x2 to x3. Okay, I should just plug in the numbers into here since we are doing this example. This is 0, 1. This is sorry. This is -1 to 0 and then 0 to 1. And then let's see what this integral becomes for this function. Okay, so we can let me just also take replace this from -1 to 1. Okay, this is better. So this integral you can actually rewrite it into two parts. So let's go here, and from first segment is from -1 to 1, and then we just plug it in 6a1x plus 2b1 square dx plus 0 to 1 6a2x plus 2b2 square dx. Okay, so for this, it's a very nice polynomial integral. We can actually solve it in closed form. So I solved it myself. Let's just not waste our time on the algebra in here. So in the end, we're gonna get this. You're gonna get 12a1 squared plus 12a1b1 plus 4b1 squared. This is the first segment, and then the second segment is gonna be very similar, minus a2b2 plus 4b2 squared. So these are this is what the integral reduces to. And for this, we can also write it out as a matrix notation using our beta. So using our beta, remember beta has all the parameters from that's a times 1, that is a times 1 vector. So we can define a matrix omega to be a A times A matrix. Then this whole constraint, then the second term can be written as beta transpose omega beta. That is our goal. Okay, so this is a very nice quadratic formula. That means we can just easily put numbers in, and then so this means here is a 12. We just this is because of a1, we have the 12 a1 squared. That means we got a 12 in here. Then we have the 6 and 6 and the 4 for this, and then we're gonna have, because we don't have any terms related to C and D, so we're just gonna put 0 in these places, and then we just fill in the second block. You can see it as a block matrix of four four by four matrices, right? So so this is going to be 12 and then -6, -6, and then a 4. All the other things are 0. So that's going to be our omega matrix. And and then you can see that if you just expand this matrix multiplication B transpose omega beta, then that will just give us exactly this integral for the penalty, for the curvature penalty. Okay, so now we can just bring everything together by writing everything into the matrix notation, both the objective function for the smoothing spline and the constraint. So this is a matrix. And then we want to minimize y minus z beta transpose y minus z beta plus lambda times beta transpose omega beta. And our constraint is a beta equals to 0. So that is a matrix notation for this problem. And I must say that here that because we are deriving everything from the 3 data points simple example here. Like when you have random intervals x, then you're gonna get get different matrices for z, beta, so for z and omega. So that's z and omega depends on x. That is different from problem to problem. Okay, now this is a very nice form of optimization we have. Let's see how we can solve it. So for this constraint problem, you can write down the Lagrangian multiplier in this way. We define L by just combining the objective, the function we want to minimize with the constraint. So we write down x L as y minus z beta transpose y minus z beta plus lambda beta transpose omega beta plus mu transpose A beta. That's going to be our augmented Lagrangian. Note that the parameter here is we need to solve our beta and mu. And this mu here, to just match the dimension, remember that our matrix A here is 5 times 8. Beta is 8 times 1. And then that means this mu here must be, mu transpose must be 1 times 8. Sorry, 1 times 5. Okay, so this means that we have 8 plus 5 equals to 13 parameters in this optimization problem. And to solve this, we are using this condition such that the gradient of with respect to beta equals to 0, and the gradient with respect to mu equals to 0 as well. So let's do that. Okay, so gradient of beta, that's going to be, we use the chain rule here, is going to be z transpose times 2 y minus z beta. And then for the second term, that's going to be the first term, the gradient of the first term. And then for the second one, see what we're going to get. Second one will have 2 times omega beta, or lambda 2 lambda times omega beta. So that will be the second, that's going to be a second term, and then the first term is going to be A transpose mu. Okay, so that's a gradient of L with respect to beta. Now for the gradient of mu, this is easier. We're just going to get A beta. So both of these terms will equal to 0. This is equal to 0. This is also equal to 0. Okay, now we have a pretty nice linear system, and it turns out we can also write it write these two equations together into one linear system in this way. We write it as a block matrix of 2 times. So we're just gonna combine beta and mu here. That's the parameter, and then we're just going to write it in this way. So this is going to be 2 times z transpose z, and plus lambda omega. And so this term times this, and then we have A transpose in here, right? And so that's going to give us the first condition, right? So this times this row here times the column is going to give us a gradient of beta. Okay, I think on the right side we also have something on the right. Okay, we have the z and y terms on the right. That's going to be 2 times z transpose y on the right hand side. And then the second one is just going to be, that's going to be easy. It's a 0 times this equal to 0. Okay. So it turns out that we can solve this whole problem in a linear system for the smoothing spline. Okay, so this result is very nice. This means that our smoothing spline problem can be solved using a linear system. So this is a linear system for with respect to our parameters. The beta we want to solve, right? So that's beta contain all the parameters for the cubic function. Okay, so finally, let's do a quick summary of what we did in this video. So for a summary, so first we start with a penalized d square. Then then we assumed the function to be piecewise cubic. Next, we write out the constraints of the problem. Constraints as a beta equals to 0. And then next we write out the objective function. We simplify the objective function as this problem as y minus c beta transpose y minus c beta plus lambda beta omega beta. So this is a penalized regression problem, and it's it actually looks very similar to the ridge regression problem, except we are adding one additional matrix omega in between the ridge term. So this is a d square. This is a penalty. This is L2 penalty. It's technically not an L2 penalty because we have the omega matrix in between, but it's just similar to that. So, and finally, this constraint problem can be solved with a Lagrangian multiplier. And that converts the problem into a linear system. Okay, so that's everything I want to talk about in this video. And for the next time, or the next upcoming few videos, we're going to talk about kernel functions, and then we're going to revisit this smoothing spline again to see how kernel functions emerges from variational calculus.